Okay, perfect. Now we start. Well, we have several attendees from different countries. Thank you so much for being with us today. Welcome to another series of Epever webinars. In this webinar, we will cover the basic knowledge you will need for calculating the size of standalone off-grid system components. And we will go through several steps to identify the requirements and the size of the components together. Well, this is a simplified schematics of a common solar standalone system. So as you can see, it has different components. If we start from here, we have solar PV arrays with different configurations. They can be in series and parallel together. Then we have a DC isolator to ease the maintenance process and to disconnect your solar PV array from your system. And then you have the surge suppression the suppression device in your system. And then we have a circuit breaker. Then we have the charge controller, which goes through another circuit breaker to the batteries. And the inverter also is connected to the batteries through a circuit connector. And again, after the inverter, we have another circuit breaker, which is an AC circuit breaker, and then we have our loads in the system. So there is a lot going on in off-grid system, and in spite of the fact that people think this is simple, but this is kind of even complicated than some on-grid applications. There are a lot of components, and you need to, if you want to design a system, you need to be aware of what you are selecting or what you are buying. And if, for example, the inverter that you selected is compatible with the battery or the charge controller tolerating the power from solar arrays or not. So these are the questions that today we are going to find an answer for. So before starting the calculations, we have to be aware of some principles, some theory behind the electrical calculations. Actually, Ohm's law is the most important law of an electrical circuit. It is the basis of almost all electrical calculations, and it allows you to calculate the current that runs through a cable or a fuse at different voltages. Knowing how much current runs through a cable is essential knowledge to be able to choose the correct cable for the system. And you can say that the resistance of a conductor determines how much current runs through a material at a given voltage, and this can be presented in this formula. So this is the resistance, this is the voltage, and this is the current. And this formula is called the Ohm's law. And power is an expression of how much work an electrical current can do. It is measured in watts, and the symbol is simply the P, and it can be calculated using the formula. Simply just multiply the voltage, the current, and then you have the power. And then some materials conduct electricity better than other materials. Materials with low resistance conduct electricity well, and materials with high resistance conduct electricity poorly or not at all. And each material has its own specific resistance, and it is measured in the ohm meter, and the symbol is rho. So you can use this formula to calculate the resistance of a piece of cable, for example, in your off-grid system. Then we have another factor. It's also the power. And when the current flows through a resistor, which could be a cable, a fuse, or any part of off-grid system, a resistor heats up. And the same happens in a cable. When the current flows through a cable, the cable heats up and the power is lost in the form of heat. And these losses are called cable losses. and the lost power can be calculated using this formula. So, but we are opening a window to this concept that if you have long wires in your installation, you are losing power somewhere, and this is going to be a big problem in your design. So every single component of an off-grid system is crucial and important, and should be chosen based on certain reason, and should be designed in a way that you have the minimum loss in your system so that your efficiency is high. And to be able to calculate the effect of cable voltage drop, you will need to know the two more electrical laws. One of them is Kirchhoff's current law, which says the current flowing into a junction must be equal to current flowing out of it. This means that if you have three passes for the current, the amount of the current that goes into the whole three passes is equal to the current that comes out. So this is the first Kirchhoff's law, and the second one, which is the voltage law, is that the sum of all voltages around any closed loop in a circuit must equal to zero. So these two rules will help us to determine what's happening in the system. So let's have a very simple example here and to see how we are using that. So you can see that we have an inverter of 3,000 watts. Let's assume that it's working in its full load, so we have 3,000 watts load in the system. And then we have a 12-volt battery. So what's happening? We will have 250 amperes current in our system. But what about the resistance in the cables? Let's just assume that the cables are the only components that have resistance in the system. So when you have 3,000 watts load, then you will have 250 amps. And if this 250 amps goes through the cables, let's just assume that the cable resistor is 1.7 milliohm. Then this will consume energy and you will have a voltage drop in your system. These are all calculatable. You see how we have calculated them. So the voltage that drops is equal to the resistance of the cable, which is 1.7 milliohms, multiplied by the amount of the current, which is 250. So you have almost 0.42 volts, almost half a volt voltage drop in this cable. And if you take it into account for the whole cable length, then you will have about 0.84 volts loss in your voltage. And what is the result of this? As a result of this voltage loss in your system, you will not receive 12 volts in your inverter size. You will only receive 11.16. And what is the result of that? When you have the voltage 11.16 and the load 3000, then your current is not 250 amps anymore. It is 268 amps. And yeah, so this is going to increase the current that is flowing into your system, and it will cause a lot of problems. And one of them could be the voltage ripples, the DC ripples in your system, because this will happen frequently, and the battery will try to compensate for the amount of the current that is needed. Then you will have a ripple, and this ripple will shorten the lifespan of all the components in your off-grid system. So with this example, we tried to demonstrate that if you have even a very low and negligible resistance in some place in your off-grid system, then you are going to have some troubles. And if you look closer to the system, it's not only the cable that has the resistance. The circuit breakers, the terminals that you are using, the bus bar on your batteries, the inverter itself, the batteries themselves, every component in the off-grid system has a kind of resistance for itself. So it should be carefully taken into account. Well, so we will try to design our off-grid system in 5 stages. First one is the daily power usage. We will first calculate how much power we need. Then we will size the battery bank. We will determine what kind of battery and how much battery do I need. And then we will find how many solar panels do we need, how many charge controllers, and finally, the specifications of the charge controllers, and finally, what kind of inverter do I need. Okay. Figuring out the amount of the power you need is the first step for designing a solar off-grid system. We need to take a list of all of the electrical devices that we are powering and how long we need to power them. Actually, for off-grid systems, we don't have anything called average usage or high usage. And based on every single consumer, the size of the system will vary, will differ. And typically, every electrical equipment will have a power label on it. So if you check the power label on equipment, then you will find out what is the amount of the power that is using in a certain period of time, like an hour. We have AC consumers and DC consumers, and based on the type of the consumer, you may see different values on the label, and regardless of the type of the consumer, voltage measured by volts, current measured by amperes, and power measured by watts. These are the 3 components that you normally find on a consumer's label. And we need to know that to calculate how much power actually we need. And there are different types of appliances, and these might be there might be variety of applications. So each standalone is designed independently based on what we have. So it could be a kitchen appliance, lighting appliance, heating, cooling, or etc. It could be any kind of appliances in your system. So here you can see an example. So you can see the type of appliances that I've entered here. And if they're running at the same time, this is absolutely the worst case, that you have all your consumers running at the same time. It really depends on your consumption style. Are you going to have all of the systems on together? And are you going to use all of them together at once? This determines the amount of the power needed for inverter, and also affects other components on the system. In this example, I have considered that I'm using the AC lights, the fridge, the TV, dishwasher, microwave, and coffee machine, and the laptop all together. And I'm running them together, and this is the quantity of them, and this is the AC watts of my consumers here. As you can see, for example, I have 2 lights of 15 watts, 1 fridge with 350, and each consumer has its own peak AC watts. So, for a brief time after being switched on, maybe that's only for a few milliseconds, electrical appliances often draw a significantly higher current than their normal operation. So it could be up to 30 times higher for example, motor loads. And this inrush current is different for different devices. For LEDs is different, for this motors is different, for PC is different. And this peak power is important when sizing the inverter. Your inverter should be capable of absorbing or providing the surge power required to have all these equipments together. Of course, it's not possible that you turn all of them at once together. So this is actually the worst case that is going to happen. I have assumed that for my fridge, I have something like 900 watts peak power. And for the others, I have multiplied the AC watts by a factor of 1.2 or 1.3. Because based on my knowledge to these kind of consumers, I know that it's not going to be really bad, or that's a good estimation for the peak power for them. So yeah, for majority of the loads, you can apply a constant like 1.2 or 1.3. For motor loads, you have to multiply it by 3, 4, 5 based on the specifications of the device. And then this is how much you are using each consumer. I'm using 4 hours the fridge. Why 4 hours and why not 24 hours? Because the fridge's system normally nowadays is designed in a way that if the temperature of the fridge comes into a certain range, then it will shut the motor down and it will not use the energy. So in average, a fridge might be working 3 to 4 hours a day based on the ambient temperature. And let's assume that we are watching TV for 3 hours and we are using our laptop for 5 hours. This might be high, but well, this is also the watt hours per day. This is for my DC lights that I have, it's 120 watts, and these are the AC watts. So for off-grid system, it doesn't matter if you are consuming a DC power or you are consuming the AC power. Although the voltage might change in a system, but the power will remain the same. So this provides you a good indication of how much power you are going to use. So I'm using 5 consumers at the same time together. I'm using total daily power consumption of 4,130 watts, and the peak power is something like 5,100 watts. I have 4,010 watts AC power consumption on average per day, and 120 watts or DC watts per day. So this was the first step of designing my system. I just wrote down what do I have, what is the wattage of them, how much I am using them, and I just added up to them, and I came to these 2 numbers, the AC and DC consumption on a daily average. So now that we know how much power we consume each day, it's now the time to determine the battery bank size. Here are the terms which determine the battery bank size. So batteries are one of the most important parts of every standalone solar system. Lead acid batteries and lithium batteries are the commonly used batteries nowadays in the market. System application, the budget, and expectations for the backup time are kind of factors that play a role in picking the right battery type for you. And the type of the batteries used in solar PV systems are deep cycle or solar batteries, which are capable of producing consistent power while being discharged to a great extent than a typical battery. For example, a car battery is capable of giving you a large amount of current, but for very short time, and the life cycle is too much shorter. The solar battery is much better in regards to the capability for providing continuous power and the life cycles. And lithium batteries also have a longer lifespan and get charged faster. They have deeper discharge rate, and this means that when you have a deeper discharge battery, this means that you will have to buy less capacity of batteries. The battery, is recognized with its voltage and capacity measured by amp hours, and to provide desired system voltage, one can wire the batteries in series and parallel. We will have another webinar in the near future about the wiring and the configuration of the batteries. And just for this webinar, it's important to know that it's not good to parallel the batteries in large number of strings. because a little voltage mismatch in strings will lead to a shorter lifespan of the batteries. And a battery bank's voltage should be coordinated with the solar array voltage to ensure the proper charging. Well, again, depending on the type of the charge controller, for example, an MPPT charge controller can regulate the voltage so that it's in range. And, well, the inverter power also plays a role in selecting the battery bank. It's one of the factors that play a role in determining the size of the battery, because not every inverter is compatible with every battery. So this is the step of selecting the battery, but at the same time you should keep an eye on what charge controllers are available in your market, what kind of inverters are available in your market. If you decide to use 48 volts system voltage, then the inverter must be available for you in the market to purchase and use it. Well, so the daily power consumption, we talked about it, the system voltage. We have different cells of the batteries, 2 volts, 6 volts, 12 volts, 24, 48. So the system voltage is really important. The higher the system voltage, the lower the voltage drops in your system. So if we go back to this example here, if you had a higher voltage here, then you will have less difference in your current. So the higher the voltage of the system, the lower the current value in the circuit, and the lower losses you will have in different components of your system. And yeah. So days of autonomy is a number of the days that you can continue using your battery bank without having the solar power available. So if it's a cloudy day or it's there is no sun in your area available, you should be able to provide power from your battery bank to your consumers. So days of autonomy could be 2, could be 3 days based on what you need and where you live and where you are designing the system for. And of course, the depth of the discharge is also used for designing the battery bank. And besides the voltage and capacity, the other primary design decision is how much to let the batteries discharge. The more the battery is low to discharge, the shorter the lifespan is. And while allowing batteries to discharge more seems to be cost effective, but this way the batteries won't last long. And deep cycle batteries are designed to discharge 80%. Well, lithium batteries are designed for discharge about 90, even 95% of their capacity. But it's recommended to choose a value, a lower value, like 80% for lithium batteries and 50% for lead acid batteries, to have a good trade-off between the longevity, cost, and the hassles of replacing the batteries. And yeah. Then also the temperature has an effect on designing the battery system, because in different temperatures you have different battery capacities. So you should take into account the worst case in the year to compensate for the temperature effects in your system. Now, of course, the inverter efficiency is also important, because just consider that you have provided the energy and you have stored it in your battery bank. But the inverter is not fully efficient. If the conversion efficiency is 90%, then you are losing 10% of what you have in your batteries. So the inverter efficiency is very important in choosing. Your battery. And well, about the temperature, you see here a table. Here you see the temperature, and here you see the different types of batteries that is normally used in the market. So when the temperature is high, when the temperature increases, this affects the chemical reactions that occur inside a battery. As the temperature of the battery increases, the chemical reactions inside the battery also quicken. At higher temperatures, one of the effects on lithium batteries, for example, is greater performance and increased storage capacity of the battery. And scientific studies claim that an increase in temperature can lead up to 20% increase in the maximum storage. So, yeah, however, there is a side effect to this. And the life cycle of the battery is decreased over the time if you use it in over temperatures. And it's also found that when the battery is charged at higher temperatures, the life cycle degradation is more significant in time. So it's really a big trade-off between what the life cycle and the capacity that you're getting while you're using the system. The cold weather also affects the capacity. Prolonged exposure to cold temperatures also has a big impact on the battery performance and the battery safety. And when the temperature drops, the internal resistance of the battery increases. So batteries have internal resistances. And when it's cold, this resistance increases. What this means? This means that it requires more effort by the battery to charge. So they will not be charged with their full capacity. And it's important to note that the loss of capacity also depends on the charge and discharge rates. So it's important that at which rate you are charging your battery. That's why you have a temperature sensor in your system for most of the chargers, and it's capable of finding the best current, the charging current, based on the temperature for your battery. Yeah, so there is a difference between the lead-acid batteries and lithium-ion batteries in regard to the temperature. It's obvious here. Other types of batteries also have different specifications. We also talked about the inverter efficiency, and it's another term which affects the battery size. There is no ideal inverter, as I mentioned, and there is always a power loss. And converting DC to AC. So this loss should be taken into account while calculating the power required for the batteries. And there are lots of conversions happening in an inverter, like to boost up the DC voltage to the high DC voltage, then switchings happenings in the FET. A lot of switchings are happening to convert the high DC to AC. And, well, there's a lot of loss. So if you check the data sheet of the inverter, you will find information about the efficiency of the inverters. So you can easily pick up the inverter's best fit for you. Of course, different inverters have different efficiencies, but you can have a roughly estimate of maybe 90% or 92% for a 48 volt DC system. This is just an example of a data sheet for an inverter, just to show that inverter efficiency is not 100%. You are losing a part of energy stored in the battery because of inefficiency in your inverter. So finally, let's just start with a formula. Here is a simple example of battery bank calculation. We have a daily consumption of 4,010 watts, if you remember from the table. And, well, we have the inverter efficiency of 90%. And then we had 120 watts of DC loads. I assume that the days of autonomy in my system is 2. So I can run my loads fully if I have, for 2 days, if I have my battery bank charged. And then you have the temperature coefficient. This temperature coefficient is actually the inverse of the temperature effect that you saw here. So for example, if you are going to use a lithium battery in 10 centigrades, then you have this coefficient, and if you divide 1 by this number, then you will get this temperature coefficient. There is a rich literature about how to find the temperature coefficient. You can always refer to the battery's manual and its specification sheet to find this temperature coefficient. And then you have the depth of the discharge of your system, and then the system voltage, which is 48 volts in my example. So what we see here, we will be needing a set of 48 volts battery that are providing 255 amp hours batteries. And if you multiply these two together, it's something about 12.3 kilowatt hours. So if you multiply this voltage to this current, you will have something like 12.3 or 4 kilowatt hours. So your batteries must be capable of providing this much energy hours per day. So minimum battery capacity in each string. Let me adjust my pointer again. Okay, the minimum battery capacity in each string is the battery bank capacity divided by number of the parallel strings. I know that I'm using a 48 volt system, and based on my knowledge about batteries, I know that I can put 4 of them in parallel together. So this formula indicating to me that the minimum battery capacity in each string should be about 64 amp hours. So if I have 4 batteries, which each one is providing at least 64 amp hours, then I will meet the battery bank requirements of my system. So this is what's happening here. This is just an example of what I have. And the final step is to determine the number of the batteries in each string, and this is calculated by dividing the system voltage to the battery voltage. So I have 4 strings, and each string must have 1 battery, and the total number of required batteries is of course the number of strings, which was 4, multiplied by the number of the batteries in each string, which was 1. So, in other words, I need 4 batteries with the voltage of 48 and with the capacity of at least 64 amp hours. So I have made this choice. This is from a company called Pylontech, and I can choose the US 3000C series. Well, these are not cheap batteries, but the fact is that this example requires a relatively high capacity. It's a 3 kilowatt system. Well, why these kind of batteries? Because the simplicity and the modularity of these batteries, which, as you can see, is the power is 3.5 kilowatt hours. So if I have 4 of them, I'm meeting the criteria that I mentioned here. I'm providing this. So I'm sure that this battery is capable of providing the power that I need. And this capacity here makes it suitable for small and large accumulation systems. It could be 1 battery for smaller systems, and they are modular, and you can put them into a rack, and you can easily expand the capacity of the system. That's why I prefer to use these type of batteries in my example. And these kind of batteries have self-designed BMS in their system, which protects the cell in a variety of aspects. such as harsh temperature, the current, over voltage, and etc. So your battery is safe. And if your charge controller or inverter is capable of connecting to the battery, then it will be, much more better, because then your profile would be smart and based on what batteries need. And they normally have high life cycles. For instance, this manufacturer claims about 6,000 cycles with 95% DOD, which is, extremely high. It's going to last, for example, for 15 or 16 years. But it's important to check how the capacity is affected for aging. For instance, what is the real capacity of the battery after 2,000 cycles or about 6 years? And these kind of batteries provide you the capability to charge, to change your capacity easily. And, as I mentioned, they are rack mounted and you can use them easily. So, in conclusion, for step 2, I need 4 batteries of this type, and I will put them in parallel because I want to increase the amps so that I'm reaching to this level. So if you put the batteries together in parallel together, we're increasing the current. This is the Kirchhoff's law. And if you put them in series, of course, you are increasing the voltage. These are the basics of battery electronics. Just very simple points about the wiring. We will have a separate webinar for this, but I wanted to mention that there is a common mistake in designing the system. It really matters how a battery bank is wired into the system. So consider this example. If you are a system integrator, you might have seen this a lot in installations. And normally people connect all the batteries in parallel together like this and then connect the one side of the parallel battery bank to the electrical installation system. So let's see what happens here. The power coming from the bottom battery will travel through the main connection leads. So it's seeing this kind of resistance. So if you consider these are the cables, and the cables have their own resistance, and this is the leads, and the resistance of the batteries itself is R, and the resistance of the cables are the capital R, then the power coming from this battery only travels through the main connections lead. However, the power for this battery has to travel through the main connections and the two interconnecting leads to the next battery. And this is the case for the next batteries. The next battery has to go through 4 sets of interconnections. The other one has to go through 3 of 6 interconnections. And what is the drawback of this? Each battery, each set of lead has its own resistance and is additive. And the top battery will provide much less current than the bottom battery. And what happens if the battery bank is being charged? The bottom battery gets charged with a higher current because it sees less resistance in its path to the batteries. And the top battery gets charged with a very low voltage than the bottom battery because there is a voltage loss here until the voltage reaches to the higher battery. And the result is that the bottom battery is working harder, discharging harder, and it will fail very soon, or it will swallow very soon. And why cable resistance is important when wiring the batteries? Because the longer the cable, the higher the resistance. Also, the cable locks and the battery connections will add to this resistance, and the resistance is not too much. I know it's about 1.3, 1.7 based on the material of the cable that you choose. But it has a significant effect. And the current will always choose the path with the least resistance. So the current coming here, of course, is lower than the current coming here, and of course the voltage. So the batteries will be unbalanced soon, and they will fail. This battery will start failing very premature. So the correct way of connecting multiple batteries in parallel is to ensure that the total path of the current in and out of each battery is equal. So if you calculate the resistance for this battery, you will see that this battery is facing the similar resistance in comparison with this one, and again this one, and again this one. So these are like the three configurations that look like better. These are the bus bars. You can use the bus bars for that, and you can use these kind of cables. And why these are twisted? Because it has been taken into account that the length of this cable should be equal to the length of this cable, so that the resistance towards all the cables are equal. So this was the point that I felt is worth mentioning here when we are designing the system. Okay, before I jump to the solar panel calculations, I would like to get a feedback from you, if you can, if I'm audible for you. Just
Yeah,
please.
thank you.
Okay. Perfect.
Okay, please.
So let's go ahead. We have now, up to now, we have calculated how much. Okay. We have calculated how much power do you need on a daily basis, how much battery do I need, and now we are going to calculate how much solar panel do I need. The power produced by solar array is measured in watts, and it's equal to the current multiplied by voltage. That's clear. And labels of solar panels contain useful information about the array. You will see the numbers like VOC and IHC, and these two are the two important characteristics we will be using in designing the standalone system. So VOC, IHC are important. VOC, or open circuit voltage, occurs when the positive and negative leads from solar array are not connected, and this will result in the highest voltage the cell can produce, and this is called the open circuit voltage of the PV array. ISC, or I short circuit, or short circuit current, occurs when the positive and negative leads are connected directly to each other, and resulting in the highest current that array can produce. Of course, these are all based on the testing conditions, which is 1000 watts per square meter of solar radiance and an air mass of 1.5. So these are the testing conditions, and a temperature of 25. Each of these elements will have an effect on these values. So when you see ISC and VOC, please note that this is based on the testing conditions in the lab. The sunlight intensity and array temperature are the two parameters which affect the produced power by the solar arrays. So solar array voltage does not change much at different radiance levels or inclination angles, but the current output is proportional to the amount of the sunlight falling onto the array. Also, temperature decreases the generated power of a solar array. That's why sometimes, you have a power loss because of the high temperatures. So depending on the properties of semiconductor material, the rating to the temperature might be different in different panels. It could be monocrystalline, polycrystalline, different kinds of solar panels. So we have the daily energy consumption. We know what's the days of autonomy. we need the geographical location to calculate the actual sun hours that you have. And then you have to know the solar panel's efficiency, if there is a shading in your system or not, if you have a tilted solar panel or not. So, yeah. We have simplified this process. Of course, you will need a very sophisticated model to exactly calculate the amount of energy that you will be getting from your solar panels. But we want to make it simple. So we are looking at a very simplified version of a formula. Well, you see that you have a daily load, then you have the days of autonomy, divided by worst sun hours of the year, and multiplied by the system efficiency. What this means, different locations of the world get different levels of daily sun irradiances, and the actual generated power from solar arrays at any location depends on the latitude, the time of the day, the season, the shading from buildings, and etc. So it's not difficult to find the sun hours. The sun hours are the amount of the hours that the solar radiance level is higher than a specific level. For example, 1000 watts per square meter. This is different for your area in the winter and summer. So it's best when you are designing the system that you calculate it based on winter, because then you will account for the worst day in the year, and you will have always energy. And about the system efficiency, well, we might wonder what is the efficiency now here. We have quite a lot of losses in off-grid systems. The soiling, snow, rainfall, voltage drops, wiring, inverter, charge controller efficiency, and, well, all of this leads to an inefficiency of 20%. So for this example, I have just simply assumed that the efficiency of my total system is, while converting from the solar DC watts to the DC power stored in the batteries, is 80%. So this indicates that I will need 2,950 watts solar panels. Again, solar panels can be wired in series and parallel, and based on the charge controller type, one can select different types of the panels. A number of the panels needed is calculated as below. First, you need to find the proper panel that you want to use. Let's have a look at it. I just assume that I'm going to use this panel here, which for me is the peak power is 380 watts. So I assume that I'm going to use this panel. I need 2,950 watts, and each panel provides me 380. So in general, I need 7.76 solar panels, which indicates that, okay, I need 8 solar panels in my system. Well, so I know the number of the panels that I need from this type, and you can see the short circuit current, the ISC and open circuit voltage, or VOC, here. For this example, I have assumed that the nominal voltage of the panels are 24 volts. You see a different voltage, VOC, open circuit voltage here, so it's not a nominal voltage. Nominal voltage is confusing for PV panels, and it is just used for classification. It's not a real voltage you are going to measure. It's not a fixed voltage either, and normally it's not mentioned in the PV specification sheet, so don't look at it. Don't look for nominal voltage for solar panels in the datasheet of the panel that you want to purchase. It's a number that we associate to solar panel to ease the designing process. A number of the cell and the VOC can tell a little bit about the nominal voltage. For example, a nominal 12-volt solar panel has maybe a VOC about 22 volts and a VMP of about 17 volts. But for sure, I know that the panel that I'm choosing is 24 volts. If you are not aware of the nominal voltage, it's better that you ask. So the number of required solar panels is equal to required power from solar panels divided by the selected panel's power. We saw this. We needed 8. Just take into account that if you come up with something like 9, you must increase it to an even number, which is 10. And yeah, these two numbers here, the open circuit voltage and the short circuit current here, are going to affect the charge controller that we are going to choose. So now we are almost determining what kind of charge controller we need. So in this example, I choose strings of 4 panels in series, and I select 2 strings of 4 panels, and this means that I'll have, well, the PV array's voltage is one's voltage multiplied by 4, which is 182 volts, and the IOC, based on the Kirchhoff's law, is 2 times 1 panel's IFC, which is 21, and the nominal voltage, array voltage, is considered to be 96 volts, so it's high enough to charge the 48 volt battery system. You don't have to worry about this high voltage as long as this open circuit voltage is in range for the charge controller. So for now, just keep in mind that with this configuration, we have 182 volts voltage on our PV array and about 22 or 21 amps ISC from our solar panels. So we are done with the solar panels, and we have we now will start to calculate the charge controller that we need. Okay, we have mainly 2 categories of charge controllers: PWM charge controllers, MPP charge controllers, MPPT charge controllers. And these are different charge controllers. There are certain differences between these two in regard to the charging technology, charging efficiency, etc. Because a PWM charge controller connects and disconnects the solar array to batteries and charges the batteries according to their voltage. This means that when the solar panel is connected to the battery, the voltage drops down, so there's a lot of loss in a PWM charge controller. But for the MPPT charge controllers, it's a kind of charging control technology that ensures delivering maximum available power. So from the solar array to the charge controllers, and unlike PWM controllers, here non-matching voltages from panels and the batteries is not a concern, because the MPPT charge controller will convert the extra power from your PV panels to the current, so that you have less loss in your system. So to calculate the charge controller, you need the wattage of the solar arrays. You already have it. You need the VOC and ISC of the solar panels. We have it. And we need to have the voltage, system voltage, which is 48 volts. So let's put everything together. We selected 8 panels with the power of 380 watts, and the system voltage was 48 volts. And then we have a safety factor. Why we have this safety factor? Because, as we mentioned, temperature affects the outcome of this PV arrays. If it's too hot, then you might have more production, and then it should be taken into account in the charge controller, because otherwise this increased capacity, this increased production will damage the charge controller. So we have a safety factor of 1.3 just to make sure that if it's really harsh condition and the environment is too hot, then we have accounted for the damages that the overcurrent might have for the charge controller. That's why we have this coefficient here, and we have 82.33 amps charge controllers. Yeah. So, and this charge controller should be able to tolerate the DOC of my array, which is 182, and should have the charging capacity of 82. So I have chosen, for instance, the Epever Tracer 10420AN. This is a series of Epever charge controllers that is suitable for high power stations, and it's tolerating considerable amounts of energy. If you pay attention to the data sheet of this charge controller, which is here, you will see that, okay, its rated charging current is 100 amps. How much do I need? I need 82. So it's already safe. And it's also tolerating something like, if I see it here, yeah, the maximum PV open circuit voltage, it's around 200 volts or 180 volts, which is almost in range. So I can say that, okay, I'm using the highest capacity of my charge controller and I'm still in range. So we are done with the charge controller. We know what we have chosen. And the final step is to calculate the inverter. The total AC watts at the same time determine the nominal AC output power of the inverter. And to obtain this number, we added up the number of the equipments that are running together at the same time and doing the same process for peak powers. So if you remember from this slide, if I go all the way back to this slide, you know how much power you're running together, you know what are the peak values of your powers. So you need an inverter that is capable of providing about 4,130 watts and is capable of providing 5K and 100 watts of energy. So here we know what is the total AC watts, we know what is the total AC peak power, we know what is the system voltage, we know what is the output voltage and frequency, because you are choosing 120 or 220 based on the location that you are leaving. And you just have to consider that it's better that you do not use the inverter with its maximum capability. So while I need, for example, a 3K or 4K inverter, it's better I choose a 5K, because using the inverter not in its full efficiency helps to be more efficient. So always take into account, for example, 25% over rating for the continuous power for the inverter. So again, I have chosen one of the Epever inverters, which is IP5000, which is capable of working with 48 system, and it's providing 5,000 watts continuous power. And yeah, it can surge up to 8,000 watts, which is more than enough what I need. I need about 5,100 watts. So this inverter pretty much fits what I have. So we are almost done with the calculations. So here is the summary. We had the list of our loads. Then we have the calculation for the battery bank, you know, the inverter efficiency, DC loads, and whatever. This is based on the Excel file that could be available for you. If you are interested, you can just use it. We came up with 4 batteries of 64 amp hours. And then these are the calculations about the required solar panel. We required 8 solar panels of 380 watts. And then this is the charge controller part. We came into conclusion that we need a 482 amperes charge controller. And finally, these are the calculations about the inverter. We need an inverter that surges with this amount and minimum continuous power of this amount, and the system voltage is this amount. So we have finished designing the system, but still not complete. Because this was long enough, so we could not cover all the concepts in one webinar. In next webinar, we are going to calculate the DC fuses required in the system, the circuit breakers. We are going to look at the wiring principles, which is really important, of the DC and battery bank wiring and the AC wiring. And then we are going to have a look at the ground, earth, and safety. So, yeah, with that, thank you so much for your attention. Thanks for being with us. And if you have any questions, my colleagues will be available for you for the questions now. You can just type in the chat section all the questions that you have, or you can send your questions via email. Yeah, that's it. So thank you, and bye-bye.